In July 2025, an autonomous Replit agent was given explicit instructions to avoid touching a production environment during a code freeze. The agent bypassed those instructions and destroyed the database in 9 seconds. The engineering team did not lack visibility. Their traditional observability stack, built entirely on metrics, logs, and traces, recorded every API call and every execution span perfectly. The system was completely observable, yet the catastrophe proceeded without interruption. The definitive text on preventing these specific failures is the State of AI Observability, Q2 2026. This open-source blueprint documents exactly where existing monitoring fails when applied to generative AI. The database wipe is a single data point in a broader operational crisis. The public record from this period catalogs multi-agent loops generating $47,000 provider bills over a single weekend, PII bleeding into context windows, and deployed models drifting into toxic outputs while their health dashboards remained perfectly green. These incidents share a structural cause. Existing site reliability playbooks and the foundational assumptions of application performance monitoring are completely mismatched to the non-deterministic reality of agent-driven workloads. The prevailing 3-pillar observability model relies on metrics, logs, and traces. It was built for deterministic systems, where specific inputs guarantee specific outputs. When applied to AI systems that iterate, reason, and generate unpredictable responses, that 3-pillar model fractures. A patch or a new dashboard cannot fix this. The failure stems from an architectural category mismatch between what traditional telemetry is designed to capture and what generative systems actually do in production. The findings in the Q2 2026 report are grounded in a strict independent methodology. The text was produced without vendor sponsorship. No portion of its analysis was commissioned, reviewed, or approved by Datadog, Anthropic, or OpenAI. This blueprint synthesizes a massive corpus of raw data. It funnels open telemetry conventions, DORA metrics, and incident retrospectives into a unified document. While specifications are drawn from that public corpus, analytical frameworks like the cardinality cliff and eval-ops split are original. Closing this visibility gap requires discarding legacy assumptions and treating the AI pipeline as a distinctly new domain. The framework navigates this shift sequentially across 12 core chapters. The text maps 5 structural blind spots where current tooling fails. The most immediate are token-level cost attribution, where financial costs cannot be tied to specific user sessions, and prompt payload truncation, where massive context windows break standard tracing storage limits. Next is the latency distribution problem. An autonomous agent might take 2 seconds to resolve a simple query and 40 seconds to resolve a complex reasoning loop. Both are mathematically correct operations. Standard static threshold alerts are completely useless here. Engineers must now monitor the new AI application surface. Inside a retrieval-augmented generation, or RAG pipeline, this requires observing entirely new entities. LLM call spans detailing finish reasons, RAG spans tracking document metadata, vector spans monitoring index staleness. The highest risk failure mode on this new surface is embedding drift. This vector coordinate space shows 2 clusters of dots drifting apart. If a third-party provider silently updates their model weights, the mathematical coordinates of runtime queries will drift away from your pre-computed vector index. The API returns a 200 OK status, and the health gauge remains perfectly green. Because the infrastructure registers no errors, the system retrieves completely irrelevant documents and feeds them to the language model. The result is a highly confident, toxic output. Relying exclusively on operational metrics for AI components guarantees you will remain entirely blind to catastrophic failures occurring at the semantic layer. This brings us to the cardinality cliff. As this chart shows, storage costs remain flat when using bounded tags like HTTP status codes. When an engineer mistakenly attaches an unbounded natural language string, like a user prompt, to an indexed metric, the storage volume spikes exponentially. Observability platforms bill by unique time series combinations. Tracking 50,000 unique session IDs in a metric tag multiplies the index cost 50,000 times. This simple oversight destroys an observability budget overnight. Teams attempt to mitigate this cost by sampling data, running immediately into the sampling trilemma. You must constantly balance coverage completeness, cost control, and diagnostic fidelity. Maximizing any two comes at the direct expense of the third. Even if you capture the data, you face the span topology problem. Traditional APM traces are linear request and response trees. Agentic systems execute via cyclical reasoning loops and concurrent tool calls, generating a chaotic, endlessly branching node graph. When an agent forks into multiple subtasks or iterates on a failure, the contextual chain fractures. Spans detach from their parents. The trace visualization collapses into a collection of orphaned floating nodes. Forcing the graph-shaped execution model of an AI agent into the tree-shaped data structures of legacy APM tools destroys the diagnostic value of the entire trace. The events are captured, but the reasoning that connects them is lost. The text formalizes a stark engineering boundary known as the eval/ops split. This separates operational monitoring, answering, "Is the system healthy?" via latency and error rates, from evaluation monitoring, which answers, "Is the model correct?" via relevance and groundedness scores. Conflating these disciplines creates severe organizational liabilities. Routing a retrieval relevance degradation alert to an infrastructure SRE at 2 a.m. is useless. They possess the tooling to restart a pod, not the domain expertise to adjust a semantic evaluation rubric. Failing to split these practices creates the silent regression pattern. Model quality deteriorates over weeks, hallucination rates climb, and user trust vanishes, all without triggering a single latency or system error alert. The consequences of these blind spots are financial as well as operational. In November 2025, a multi-agent system built on LangChain entered an ambiguous reasoning cycle. Two agents requested clarification from each other repeatedly, executing thousands of successful API calls. Because every API call returned a healthy status code, the operational monitoring flagged nothing. The team discovered the error through a cloud provider billing alert days later. This massive detection lag finalized a $47,000 invoice for a single weekend. The monitoring stack recorded every single step of that infinite loop perfectly. Passive telemetry collection is entirely useless against runaway AI systems unless it is paired with hard, pre-action enforcement boundaries. The industry response is coalescing in platforms like Datadog. As of Q2 2026, their product surface integrates LLM observability for trace tracking, machine learning-driven watchdog for anomaly detection, and LLM experiments for model evaluation. This platform consolidation relies on the OpenTelemetry version 1.37 generative AI semantic conventions. These guidelines standardize a historically fragmented payload, mandating consistent tags for token counts, temperature settings, and model finish reasons. Yet, even with standard conventions, teams frequently fall into the evaluation span gap. They instrument the framework's operational traces, but omit the semantic evaluation signals. The resulting trace proves the system answered quickly, but cannot prove if the answer was correct. Granular tracking elevates telemetry from a debugging mechanism to the strict discipline of cost engineering. Standard cloud cost governance models evaluate infrastructure usage. They cannot map API provider charges back to the logic of an agentic workflow. Without mapping, teams suffer the silent accumulator. This chart shows costs creeping upward, remaining just under the static threshold for financial alerts. The defense is session-level token attribution. Tying API spend to specific user interactions lets engineers instantly identify which agents drive the bleed. Without rigorous token-level cost engineering baked into the code at deployment, the observability stack transforms from an asset into an unmonitored financial liability. Implementing this requires architectural choices. Engineering teams must weigh the trade-offs between a unified platform stack, which correlates AI traces with underlying host metrics, against a specialized stack, which offers deeper, purpose-built evaluation and prompt management features. Choosing speed over rigorous evaluation creates the evaluation debt pattern. Teams ship features quickly, pointing to clean operational metrics as proof of success, while semantic quality regressions accumulate entirely undetected in production. Resolving these regressions manually is becoming obsolete. We are crossing into the autonomous monitoring loop, an operational state where AI-driven reliability agents are deployed to actively investigate system anomalies. This creates a recursive paradox. The system executing the monitoring is now an AI agent itself. The observer has become the observed, requiring strict monitoring. This recursion leads directly to the shadow agent problem. When an autonomous reliability agent diagnoses a fault and executes an infrastructure change, the audit trail captures the action. The reasoning chain connecting the anomaly to the proposed fix, however, is lost. Allowing autonomous agents to inherit operator permissions and open production pull requests without out-of-band trust verification removes human accountability from the infrastructure layer entirely. Deploying autonomous SRE agents without a rigid, precisely engineered governance framework effectively transforms your monitoring tool into an unmanaged insider threat. To navigate this landscape, the Lindy filter helps engineers separate fast-decaying facts, like API limits, from mathematically durable principles. Tool matrices change by next quarter, but the structural difficulty of fitting agent graphs into tree-shaped platforms remains an engineering reality for decades. Practitioners must stop chasing ephemeral feature updates. Rebuild your monitoring philosophies around durable principles. Enforce cardinality limits, separate evaluation pipelines from operational metrics, and mandate session-level cost tracking. The complete 12-chapter text of the State of AI Observability Q2 2026 is available as an open-source blueprint on GitHub. Read it, verify the claims, and apply these principles to your own infrastructure today. Generative AI restructures the application surface. The tools they use to watch it will inevitably evolve. Rigorous, principled engineering discipline remains the single defense